Just to go over things, these ridiculous 10-week quarters that we have are so incredibly short, and there's still a lot of material that we have to get through inside them. We're finishing up the lecture where we're talking about parallelism, which is lecture 16, and we'll be starting on lecture 17, which is posted on Piazza, which deals with the distributed database. And then and we'll be finishing that probably next time. And there are two lectures that I'll be posting, one having to do with telling you more about log structured merge trees, and the other talking about spatial database and a structure called an R tree, which is used for accessing, and we'll see about whether we get to those. The material on parallelism that we nearly finished last time, and on distribution, which we will nearly finish today, are both on the final, but the material about LSM trees in lecture 18 and about spatial database in lecture 19, whether or not I get to them, those will not be on the final. So you've got a map of how the remaining lectures in the term go, three lectures left. And we talked about a bunch of things about parallelism last time, and where I left it, and just remind you about it, is that in systems, not just SAP HANA, but in parallel systems, modern parallel systems all over, have parallelism at many different levels. And I also wanted to remind you about NUMA when we talk about what's going on in parallelism, again, not just in HANA, but in a database. You've got parallelism going on because there are lots of different users who are doing things. You've got parallelism because inside a query, you could be doing your bushy join where you join A join B, and in parallel, you're joining C join D, and those in turn get joined together somehow. But there can also be pipelining of stuff that comes from the result of one operation moving into the result for another. Although pipelines get blocked, for example, in aggregation, you can't tell what the sum is and move on until you have all the values that you're summing together. So that's the way the pipeline can get blocked. You can end up having data partitioned on a number of different systems, or even across a number of different CPUs. And lots of memory, so where the data is located and how the data gets accessed. There's always the question of where is the data and where are the instructions, and do you bring the instructions to the data or the data to the instructions. But a lot of things can be on in parallel. You want to make sure that you never end up being delayed waiting for the data to reach you, and also that you don't overload the data. And what I pointed out last time is even if the data isn't partitioned into, let's say, 100 different parts, you can stick your finger into the data at 100 different places and have different threads that are working with 1/100th, let's say, of a big file, and doing work to select the tuples that correspond to location as California or whatever complicated predicate you have, and you can do that even with joins. So all of that ends up being great. You can also do not just searching, but also aggregation in parallel. So what you can do is you can get the total of the salary for lots of different departments in parallel. If the data is partitioned by department, you can get the total for each department in parallel easily. But even if it's not partitioned by department or sorted by department, what you can do is you can add up the piece for engineering and for marketing and for sales and for shipping. You can add that up at each location and then put those back together again to figure out the total salary, let's say, of the engineering department. You get the total salary of engineering in 12 different places. You add that up, and you get the total salary for engineering altogether. There also is multi-threading that goes on in Intel processors, where you can have hyper-threads and so on going on. And I'll remind you about what goes on with NUMA. There's a lot of stuff that happens, as we've talked about, where the closer the data is, the better the locality that you have. With these different cores, is the data in RAM, or is it is it on the board? Is it on the chip? Is it in the CPU? Is it on the core? The closer the data is, the better. And what Intel will do is it will move data if it's seeing that you're doing sequential access. It will move the data closer up to you, not waiting necessarily for you to ask it. It will see the pattern of your access, and it will sometimes see about moving data up to you to access, and that works well. The last thing that we talked about is vector processing, and as I pointed out, you can do, if you have 6 bits, right, and say 6 bits allow you to encode values up to 64 values, since 2 to the 6 is 64. You could fit 5, or actually 5 1/3 values inside a 32-bit word. And Intel processing has vector processing. You can do comparisons. Let's say if you're searching for all the things where location is California or salary greater than 10,000. If all you have is 10 bits, you won't for salary greater than 10,000. But you can do comparisons, again, for location is California, and there are only 50 states plus a bunch of other locations if you're just looking for state. You can do that, and you can do not just 5 comparisons in a clock cycle, but actually even 5 1/3. So you can take advantage, and you'll do 5 1/3 in each clock cycle, so you can go faster than clock speed to be able to do operations. So there are lots of different levels at which the parallelism occurs. And emphasis here, as hardware keeps changing, and there's a feedback loop here. Intel knew that databases were looking at trying to do searches faster, searching through data. And so the operations that they made available explicitly that you can write and implicitly that are going on behind the scenes, they talk to database companies. They talk to companies all the time. They have people who work at Oracle who are Intel employees. They have people who work at SAP who are Intel employees, etc., who co-author papers together about how to make all this stuff work. Because Intel cares about selling lots of chips. And so having things that work well for the really important applications, and database is a really important application. Data management in general is a reasonably important operation, even when it's not even a full database. That matters a lot. So databases try to use Intel hardware cleverly, and Intel changes its hardware so that the database companies will say, oh yeah, we really love Intel hardware. We can get great performance out of it. I mentioned earlier that indexes are less important than they used to be, because the ability to be able to access things via lots of parallel sequential searches is really, really good. It doesn't mean indexes aren't important. For example, for uniqueness, it's great to have an index to be able to figure it out, especially if you can have your tree kept in cache, your B tree index kept in cache, except maybe for the lowest levels. But sequential search and sequential aggregation is really fast. Used to be that SAP kept lots of interesting aggregations that people cared about around, but then you have to update those aggregates if you're keeping track of them. Aggregates are still kept sometimes, but far fewer, just as with indexes, because aggregation is so fast, and this way you don't have to guess which aggregations are they going to care about. This way you can go really fast on all the different aggregations. It's not as fast as if you stored it, but you don't have to keep updating your aggregates all the time. So emphasis, hardware changes, algorithms change to work well with the hardware, engineering changes to work well with the hardware, and the hardware changes to work well for the particular applications. So the theme here is the world keeps changing, and it will continue to keep changing. So summary, parallelism is great for query processing. It was the good fortune that database is set-oriented and it's functional, and meaning it doesn't have side effects, right? It's huge, and it's declarative. It's hugely a great match for parallelism, because you just come up with a plan that takes advantage of it. So it was really a great approach. You have the shared nothing approach, which again, it's the embarrassing parallelism. A lot of the stuff with Spark and Hadoop works really well with shared nothing. You spin up n different things in work, but it means that you have to be able to work with shared nothing, and moving things around gets complicated. Shared memory makes programming very, very easy, except implementing things that end up scaling well is a lot more complicated. So shared nothing is cheap and scales really well, but unless things are embarrassingly parallel, it ends up being harder to program. With shared memory, you can program as if it was a single computer. It's just a matter of having an implementation that can work well to provide that illusion. There's parallelism at 17 different levels in databases we've talked about. How you actually partition the table, you're not going to have 17 copies of the data partitioned by all the different things that you can partition on. You have to be able to figure out how you choose to partition, and partitioning can work well for some queries, not so well for others, just like indexes may work well for certain queries, not well for others, and you have to update the things. So how you split things up ends up mattering. Database operations, including joins and so on, and sorting and aggregation are, again, easily parallelizable. Database, again, is a great application for it. There are all these complex plans. There's parallelism at lots of different places. Pipelining is terrific, but certain operations block the pipeline. You need your sort in order. Well, that blocks the pipeline until your sort is actually done. And again, bushy trees help allow you to have yet another basis for parallelism. Doing this, doing A join B, join C, join D in parallel, and then joining the results together. Perhaps the hardest part of getting parallel database going is figuring out how expensive is this stuff. Again, optimization, you have incomplete statistics. You gotta keep track of what the join cardinality is for A join B whenever you have whatever subset of A and whatever subset of B and whatever join predicates between A and you have cost formulas that are slightly bogus. You have situations where you have statistics that are not kept up to date. A great, as we've talked about before, learning optimizers that take the most common queries and try to figure out really good ways of optimizing them, especially when similar or almost the same queries are run lots and lots. There are lots of different things you can do to make that better. We haven't talked about where parallelism comes in transactions and logging. When you have a shared memory architecture, it's relatively easy to make things work as if there's one system. Locking gets much more complicated in a shared nothing architecture. And again, we talked about a couple of different ways of having our secondary indexes. Having a global secondary index is great for uniqueness, and meaning an index that's different from the way you partition the data. It's great for uniqueness, but it makes it more complex when you're trying to go ahead and do the updates of the index. So again, a global secondary index is great for maintaining uniqueness. Local secondary index do support parallelism very easily because you can search each location for things where location equals California or salary greater than 10K or all the rest of it without having to bounce around so much. Again, so optimization is hard, database design is hard. There are lots of issues about scheduling for the combination of OLTP and OLAP that's going on that ends up being hard. There are questions about all the utilities you want to do. How do you back up in parallel? Heck, how do you even do checkpoints in parallel? How do you create indexes in parallel? There's so many different things that are great topics that we haven't talked about in this. And there are all kinds of issues about getting the applications to be able to work well when you have particular database applications. There are lots of different companies that have worked on it. And you also have, again, I will emphasize, it's not just databases anymore. There are so many different things that are going on that do data management without transactions, and the idea is you have this huge amount of data that you want to be able to work with in parallel. I mean, you've got billions of things at Facebook. You've got, all these different things. The amount of data people are working with is huge, and a lot of the stuff I've mentioned that the things that we do with MapReduce are very similar to what we've already talked about with aggregate and group by. And again, there are more complicated things that are going on with data science, but you take advantage of a lot of techniques that exist in the database. I'll give you an example. Spark focused a lot on saying, well, we're going to deal with file data and we won't assume that things have a fixed format. Turned out that a lot of data has a fixed format. And so they also have a set of things where if they can figure out that the data has pretty close to a fixed format, they'll optimize based on a lot of database techniques. So again, database techniques aren't used fully when you're looking at a lot of the so-called big data situations, but they're used with variations. all the way through. Everything that people have done in database has been rediscovered and reinvented, often with credit, in this other big data world. But of course, there are differences in that world. It's not the same as what database had. Questions about parallelism before we start distributing? Okay, distributed database. And again, so project 4 is due on Thursday. Everybody knows about all that stuff. Base it on our project 3 solution if you want to. You know about the story with respect to your teams. And the final exam, again, is a week from Wednesday in this room. Covers the entire quarter, could cover any material from the projects, but I won't be asking you to write CC+ programs during the final. I did post a previous year's final, but not the answers. There was an early question about one of the things on the final. I haven't gotten a lot of other questions on it. I'm actually surprised. I've expected to get more questions since there is no answer sheet for the final. So if you have questions, post them on the Piazza. I'll try to answer reasonably quickly. You get to bring in the cheat sheet. You can't bring the book, can't bring notes, but you get to bring in a single cheat sheet, whatever you want written or printed on both sides. And of course, there are these evaluations that are going on, campus-wide things that are now called sets. That should be a clickable URL, but you should know messages about these things that are there. We can never identify individual responses, and the aggregate responses don't get made available until, you know, a month after, you know, these things close, so it's after grades are in, all the rest of it, and constructive responses can end up helping. So anyway, we've talked a lot about what goes on in all these different parts of the database. We started at the bottom and we built ourselves up, including looking at what can be done most recently in terms of parallelism inside a system. What if you have more than one database? There are lots of reasons why you might have more than one database. What can be done when you have more than one database? And we're going to talk about some of the things that can operate there. Now, there is the notion that you should, this was something that started with a system at IBM that was called R-star, and frankly, it ends up partially getting ignored now, even more than partially. There's a notion that you'd like to be able to write queries, and if there are a whole bunch of different databases, you may not need to know where the database is, or even that there are 17 different databases. So I decided to split up my data into 5 different databases to be able to get separate performance and have one database for the North region, one for the West, one for the East, one for the South, one for the Central. So I've got 5 databases, and the data from those databases can be put together. And they have their own transaction managers that are working. But I still want to have a transaction that crosses the boundaries of those databases. Or I might have a company that buys another company, and now I want to do things. I haven't changed everything in the new company's thing to the old company's schema. I want to do transactions across boundaries between these things. We'll talk about ways that you can do it. And I will also tell you a little bit about reasons why you may not want to do things that way. So there was the original idea, let's have people not even having to know what's distributed in which database. It tends to be a little less important than it used to be. But the notion of physical and logical independence still is something that people used to talk about. You know what? I mean, in a world of microservices, people, there's more notion of having separate databases and not necessarily doing transactions that cross database boundaries. We're going to talk about how you can provide that, but I will be all the way through emphasizing that there's a price that you pay by not having transactions that cross database boundaries. And there's a price that you pay when you have transactions across database boundaries. And I'll give you the punchline to begin with. What's the price that you pay when you do distributed transactions across multiple databases? Oh boy, it gets complicated and expensive to be able to do for various reasons. What's the price that you pay for not doing transactions? You don't necessarily have consistency. And again, I can't always explain why. In fact, I infrequently can explain why. But people are willing often to say, I'm going to do A in this database, and then I'm going to do B in this database, and then I'll do C, and if I have trouble with C, then I'll see about doing something back in B that doesn't undo B, but does a new forward-going transaction that says, oh, the guy didn't make this hotel reservation, I'm canceling it, or stuff like that. So I will be showing you how you can do distributed database and have things where you can do transactions across databases, among other things. But a lot of what goes on these days says, I'll do A, then B, and then C. And if C doesn't work, I'll roll back C, and I'll do something at B that doesn't undo B, but rather does something that goes forward that says, I'm canceling this guy's reservation or something like that. But the principle in distributed database is you don't necessarily have to know where things are. And principle in distributed transaction atomicity is you want to write transactions that go across multiple sites. And again, with the understanding that you don't necessarily always want to do that. We'll talk about what the mechanisms are by which you do it. We'll talk about a lot of aspects of distribution. So basically, the recent trend is that people do need to know where things are. R-star tried to hide the location, tried to make things look as if it was a single database. It didn't really catch on. So again, this notion of where things are located, it's much more visible. And so really trying to give independence and so on, it's just too expensive. And again, administrative stuff gets complicated, and more importantly, performance gets complicated if you really try to go for that. So when you do have distributed database, when you do have multiple databases, there are two possibilities. One is that every site is running the same type of DBMS. Everybody's running, SQL Server, everybody's running Oracle and all the rest of it. And that actually makes life a lot easier than if you have the heterogeneous case where you're trying to do transactions across heterogeneous sites where they may be multiple different vendors of the RDBMS with their own different, transaction managers and all the rest of it. It still is possible. There are standards for doing distributed transactions across different database managers. But what I will emphasize to you, and I have already, is that there's no standard for logs. The Oracle log looks nothing like the DB2 log. Well, it has the same kind of ideas underneath it, but it's not the same format. Looks nothing like, the Microsoft log, Oracle log, IBM log, the Postgres log. They're all different. So it's not as if one system can read another system's log records. But basically, there can be ideas where you can have databases that are still capable of talking to each other because they're all speaking SQL, and there are transaction management standards that allow them to be able to work together. So basically, if you're trying to go ahead and do distributed database, one way of doing this is you have a client who talks to a whole bunch of different databases, and another way of doing it is that you have a query that goes across, multiple different sites. So basically, it could be something where the client talks to this database, and the client talks to that database, and so on. Or you can end up having something in which you have a client that ends up talking to one server that in turn may end up talking to a whole bunch of different servers. And there are a lot of different variations of this that you can play with. And how does the data end up getting stored? Now, this is most likely to happen in a case in which you have a homogeneous system, in which you have all things being Oracle or something like that. You can split the data across different sites. So as I mentioned, you could have Oracle database systems where you have north, south, east, west, and central regions. So you've got 5 different databases, and you want to be able to do things across them. And you don't want to have one different database system because that might get a little bit overloaded or something like that. And you also want to have locality of the databases to the individual regions. At least that used to be important. So you split the data across these 5 different databases. And how do you go about splitting the database? How do you fragment it? There are 2 different ways that you can do it. One corresponds to what we've already talked about as sharding. The other is a little bit different. We'll talk about why both of these are useful things to do. Number 1 is you can do what's called horizontal fragmentation. That means I'm going to keep the rows that correspond to the east region. I'm going to keep them in the east database. And the north one's in the north database, and so on. So I'm going to split based on the region field that I have inside my data. I'll put things there. Or I could split on other things. Customer numbers up to 1,000 can go in this database, and between 1,001 and 2,000 in that database, and between 2,001 and 3,001 in that database. So I can split the rows based on the values. By the way, it doesn't say that I need to store it in row form. It says that I'm splitting the things of the data that corresponds to this range of values is here, this range of values is there, and so on. And when I'm doing that, typically I have disjoint sets. So I don't have the north and the south, and I will have the things between 0 and 1,000 and 1,001 and 2,000 and so on. Those will be in different locations. I typically won't replicate and have, let's say, the things between 990 and 1,012 sitting in 2 different places. You could do that. It tends to be unusual to do it. So I'll have things in what we're talking about here in one different place. There's another way of splitting things up, which is kind of interesting. Let me describe a situation that's very real to you. I have the columns that I access a lot, the hot columns. And I have medium temperature columns, I access them sometimes. And I have cold columns that I almost never touch. What happens when I bring an entire row into memory where I bring in all the columns, including the cold columns? Let's make it simple, and let's say it's 1/3, I have 1/3 that's hot, 1/3 that's warm, and 1/3 that's cold. If I bring in a whole row, and I'm bringing in all these different columns, I'm contaminating my memory with, and including my caches, with a bunch of data that I don't care about for this particular query. Maybe I can get rid of some of the columns, but I'm filling things up with a bunch of columns that I typically won't need. So there's another way of splitting up my data. I'll have 3 separate tables. One that has the hot columns, one that has the warm columns, and the other that has the cold columns. And they'll all have the primary key or the TID, whatever it is. There'll be something that allows me to be able to join them back together when I want them. So let's say I just have the primary key for each. So if I want the entire tuple, then I can look it up and then get not just the hot columns, but also the warm and the cold columns by joining them together based on either TID or primary key or something like that. That allows me to get the entire tuple. Question?
So, just how do you determine these hot, cold, and how do you determine which column is which? I mean, are you keeping an aggregate? Because that seems like it would take up some memory and you'd have to update that every single time. And how do you know if it's going to stay a hot column? And how do you change that?
Okay, that is a wonderfully detailed question. I'm going to give you a short answer, but the long answer would take, basically showing you a bunch of discussion over it, some of which is proprietary. But generally, here's a couple-part answer. Generally, people know which columns they look at, but you can also do analysis of the queries that are being executed and how often they're executed and what things they end up doing. So I mentioned that database systems keep track of all sorts of different things. You're right that if I was trying to update every time I executed a query, it would be expensive, but you can do analysis of things that are a little bit more offline. So you can do analysis, for example, of the logs to be able to see parts of what's going on in terms of the updates. You can do analysis of programs that are being run, how often they end up being run. There's a huge amount of data that gets collected while things are running, but it's not necessarily kept transactionally. So what you could do is you could be counting inside memory how often certain types of queries end up getting executed. Doing no analysis of it, but just counting it and lazily writing it out to persistent storage as you go. Maybe even sampling it as you go and keeping track of it for every kind of query or something like that to be able to get some idea of what the analysis is. In other words, there are all sorts of approximate ways that people can use, and there are enough square cycles and there are enough processors that what you could go ahead and do is keep some kind of reasonable analysis of what's going on. You're pointing out that the load could end up changing a whole lot, and that's absolutely true. It's also true when you're trying to figure out about good ways to optimize, based on what parameters you have on queries and all the rest of it. All these things are interesting. The answer to your question is it's hard, like any other aspect that relates to scheduling and optimization and all the rest of it. And what usually ends up happening is that there are some clever techniques that are approximate that get used that seem to be good enough for various types of situations. And I know that this is not an excellent, wonderfully detailed, professional description of what the answer is. It does have the virtue of being approximately true. I mean, all you can do is talk to people, analyze based on approximations of, here are my query space, here's how often the programs are being run, and all the rest of it. Keep track of everything, which can end up being expensive, or keep track of enough to be able to give you a reasonably good answer. Everything that I just described is used to some extent. And again, as there are more and more resources trying to actually do the analysis, it pays to do the analysis, because it used to be spending a lot of time keeping track and thinking, the Hamlet problem, think versus do, right? Always seem to go in the direction of let's do it and let's not worry about it, and we'll do some gross analysis afterwards what the problem is. More stuff, the amount of stuff that is tracked and stored in the catalogs approximately, as I mentioned before, ends up being huge. Because you can. Hillary, what did he climb? What did he climb Everest? And again, as time goes on, different things are done. It's a great question. This is the best answer I've got. Okay. There's another approach. So again, you can always put together the whole tables based on basically joining them together. There also is the question about having multiple copies of data, and this is part of distributed database too. Now, why do you want to have multiple copies of the data? Reason number one, availability. If something goes wrong with a copy of the data and you have another copy of the data available, you can keep running, and there's a principle, a really key principle, the show must go on. Businesses want to keep running even when there are problems. Consistency is really important. Keeping your business running is more important, and dealing with problems, and again, the techniques for dealing with problems, there are some reasonably well-known, it's a pain, but stopping your company from running, because I don't like what's going on here, I'm going to stop the company from doing any business for an hour. It costs a whole lot of money. You want to keep taking orders, you want to keep doing searches, you want to do whatever it is that you're doing, even when there's a problem. Replication can help with that. Replication can also help with performance. How does replication help with performance? I've got data that I need to be able to look at, and I've got my 5 regions, where things are going on. Network speeds have gotten better, but the speed of light isn't, just a good idea, it's the law. And there are still limits on network speeds. Again, things have gotten a lot faster than they used to be. But looking at a copy of the data that's local will be a lot cheaper than looking at a copy of the data that's 3,000 miles away. So you get an advantage because of performance. Okay, so again, that makes things run faster if you have a local copy of the data. Another advantage on performance is I can store the data in different formats. For example, suppose that I store the data in row format in one place, and I store it in column form in another. Row tends to be better for OLTP, column tends to be better for OLAP. Remember these data cubes and star schemas and so on we talked about in 180. By storing the data in multiple formats, and there are lots of different formats besides that one, then I can direct a query where one format is better to a place where it's stored in the better format. And so that can end up being an advantage. There is two minor problems with having replicas. Replicas are wonderful. I've just explained why they're great. So why are they bad? You have to keep them up to date. It's like indexes. Having replicas is terrific, but you have to keep them up to date. And we'll talk about a couple of the techniques for dealing with that. What's the other disadvantage of having multiple copies of the data? Well, you not only have to keep them up to date. When does your write finish? I've got 5 copies of my data. Do I say my write doesn't finish until I've updated all 5 copies? Well, that's great for availability. I can't do any writes if one of them is down. That's not acceptable. It's a great way of achieving unavailability instead of availability. False. Talk about pessimistic. That's not going to be good. Also, it takes me a while, even if I say 4 out of 5, or as we'll see, maybe 3 out of 5. It slows things down if I wait until at least 3 of my copies are up to date. So again, updating my local copy, I may be able to do fast. Updating 3 out of my 5 copies, that's gonna end up increasing latency. So there are issues with replication. One of the approaches, let's just take the case in which I have 2 copies. This is an approach that database systems have used for a very long time. There are newer techniques, I'll allude to some of them. But suppose that I have a primary copy and a backup copy. And the idea is, if there's the failure of the primary, the backup can take over and continue processing. Do I wait until the backup has the current data before I let the primary go forward? That slows things down. If I don't, when the backup takes over, it might not have the current data. Really difficult, interesting trade-offs. What if the backup goes down? Do I, out of my high availability having a backup, do I say the primary can't do any operation because the backup hasn't acknowledged the update? Not good. Not good. So an approach that people sometimes say is, I will do the update at the primary and I'll asynchronously send. I'll wait until I've sent the message to the backup so it will reliably get there, but I'll regard that as being okay even if it hasn't entirely gotten there. So there are lots of different trade-offs on this which end up being complicated. Now, we're going to talk about distributed catalog management. And think of this as just being distributed data, metadata. I need to know what the metadata is across all the database systems that I'm managing so that I can go ahead and do optimization of queries that may be touching multiple sites. So I need to be able to, in distributed database, the idea is that you can go ahead and identify data by its birth site. So instead of just having something where you have, let's say, a table name, maybe schema.tablename.column, whatever, I will say birth site.schema.tablename.column-name attribute name. Why do I say the birth site? I have an idea of where the table or partition of the table was created and born. And the reason that I have the birth site rather than the current site is that there was a notion that data might be moved around. So there's a place where the data started off, and even if it's not there now, I'll be able to know where it is currently, because the birth site will give me information about where it's currently located. This is a whole lot like forwarding addresses. You have a universal name that you can always use to refer to, a piece of data like a table. And if it gets moved to another place, then you'll be able to get metadata about where it moved. So all this stuff is there and allows you to play with it. Not used that much anymore. But just to, again, take a simple example of this, you have queries. And you have to deal with data which may be fragmented into different pieces, may be broken up, either horizontally, split up the rows in different locations, or horizontally split up the columns in different places with a join column to be able to put them together. So if you have this query, you're selecting the average age of sailors, where the sailor rating is more than 3 and less than 7. Okay, so if we're splitting by the rating, and suppose the tuples that have rating less than 5 are in Shanghai, the tuples greater or equal to 5 are located in Tokyo, then what I can do, and it's a lot like what we talked about with parallelism, but it's distributed. What I can do is I can go ahead and get the sum of the ages at Shanghai, but for the ones that are greater than 3, I'm doing this query, but I have to look at both Shanghai and Tokyo. So I'll get the part of the query that I need in Shanghai, the part of the query that I need in Tokyo. I'll get sum, I'll get count, and I can put together average by adding the sums, adding the counts, and dividing. Okay, and again, as with the partition pruning,